The world emits around 40 gigatons of CO2, which is a huge amount. So where do I store the CO2, even you capture? The best solution is to not only capture but convert that captured CO2 into useful chemicals.
What made you decide to use nanochemistry to solve environmental problems?
The beauty of nanochemistry is by simply changing the size, the shape and the morphology, you can change their properties.
Can you tell us more about that?
If I take a bulk gold, you need to heat around 1200 degrees Celsius to melt. But if I take a, say, 2 nanometer gold, I can just rub in my hand and it melts.
I'm curious to understand how you convert CO2. What is the process? Could you take us through it?
Yes.
This is the Boring Climate Podcast, a platform where we encourage serious climate conversations. I'm your host, Vishwada, and today's theme, the big CO2 question. A lot of the global warming is caused by rising CO2 levels. And these CO2 emissions in our atmosphere stem from the combustion of fossil fuels in our everyday lives. But what if we could capture the CO2 and convert it into a valuable resource? Today's guest is doing just that with his groundbreaking research. Dr. Vivek Polshettiwar is a leading researcher at the Tata Institute of Fundamental Research here in Mumbai. From a small village in Maharashtra's Vidarbha region to winning one of India's highest science awards, the Shanti Swarup Bhatnagar Award in 2024, his journey has been nothing short of inspirational. After finishing his PhD in 2005, he worked as a postdoc in France and the US before starting his independent group at KOST in 2009. In 2013, he moved back to India to join TIFR, where his Nanocat group develops novel nanomaterials that work as catalysts to combat climate change. Join us as we try to understand more about his work, CO2 conversion, and its application as a climate solution. Welcome to the show, sir.
Thank you.
To start off with and to set context for our listeners, three brief basic questions. Why convert CO2 and not just capture it? What is catalysis and what is nanocatalysis?
Okay. First of all, thanks for coming to TIFR, and I'm more than happy to discuss about the CO2 capture and conversion and its usefulness in combating the climate change. So, we all know now the climate change, the global warming is because of excessive CO2 in the environment, right? And I think everyone can think of like this, that let me capture all the CO2 from the environment and it should solve the problem. But one has to understand the scale of the CO2 that we emit. The world emits around 40 gigatons of CO2, which is a huge amount. So where do I store the CO2, even you capture? Capture itself is extremely difficult, it's energy demanding process. But somehow there are ways nowadays to capture the CO2. But then captured CO2 has to be stored in, say, empty oil well or some other porous lands and somewhere. And the basic chemistry of CO2 is such that CO2 is non-reactive, so it doesn't really strongly bind with any surfaces. So they are there loosely bound. So what will happen? They will leak by maybe because of earthquake or some changes. They will leak, and if they leak, what will happen? The large amount of CO2 will suddenly come into the environment, and that will have a huge impact onto the climate change and global warming. So therefore, the best solution is to not only capture but convert that captured CO2 into useful chemicals. So think about this, that you have such a huge amount of CO2, and CO2 has the carbon. And if you look around us, majority of things is made up of carbon. So can I now not make the CO2 as my carbon source? So I take the carbon out from the CO2 and make different chemicals, right? Whatever you need, say polymers, methanol, ethanol, fuels, petrol, diesel, even steel, the carbon steel. Even there are ways to convert CO2 into cements. So that will not only solve now the problem of excessive CO2, but it now becomes some sort of a source to make different kind of materials that we need every day. Now, if this is really true, then why are we not able to do that? Why are we not able to convert CO2 into useful chemicals at industry scale? The reason is CO2 is extremely stable molecule. In chemistry, it's extremely stable. So if something is extremely stable, why will it convert into some other molecule? It won't. It will remain as is. So that means now I need to put in lots of energy to convert CO2 into some useful chemicals and products. Now energy required to convert is higher than the product that I'm going to get. So the economics will be wrong, right? You will not able to make economical processes. And that's where the role of a catalyst comes in. So what we generally do is you develop these materials. Catalysts are ideally materials which has a high surface area, high surface energy. So then they capture the CO2 onto their surfaces. So when the CO2 sits onto these nano surfaces, the surface stretch them, bend that molecule at a molecular level, and that makes CO2 extremely reactive now. So now the energy required to convert CO2 into some useful chemicals is less, and that entire process can be now economically viable. That's the role of a catalyst in CO2 conversion.
Right.
Yeah.
Before we get deeper into how you do this, what made you decide to use nanochemistry to solve environmental problems?
Okay. So see, we have to design a new materials with a proper function, right? Function in this case is activating the CO2. Then I also want to add hydrogen into the CO2 if I want to get a methanol or a methane or some other molecule. So I need to have a surfaces which can activate hydrogen. I also want to do this thing using solar energy. So I need a surfaces, or I need a material which can harvest solar energy. Now the question is, how do I tune the properties of the material? How do I design so-called new material which is unknown to us? So there the concept of nanochemistry helps. So see, for example, all of us uses this gold jewelry. So gold is very shiny yellow color. The reason is gold is metallic. It has this electron cloud onto the surface which you don't see, but they're there. So when light comes and hit the gold surfaces, the light photon, then the electron cloud on the gold surface reflects all the light except some blue portion, and that's why you have this very shiny gold color. But when I change that gold, bulk gold, into a nanoparticle of say 1 nanometer, 2 nanometer, 10 nanometer, then I can make gold of a different color, blue, green, red. So this is one of the example of the strength of a nanochemistry to tune the properties of the material. And now I am able to change the optical properties of the material. If I take a bulk gold, you need to heat around 1200 degrees Celsius to melt. But if I take a say 2 nanometer gold, I can just rub in my hand and it melts. So now you are able to change also the physical properties. So the beauty of nanochemistry is by simply changing the size, the shape and the morphology, you can change their properties, which is just impossible by using any other techniques that we have.
Right. So I'm curious to understand how you convert CO2. What is the process? Could you take us through it?
Yes. So see, the best possible process is that you should have some sort of a tube filled with a material, a catalyst, and you pass the CO2 and water, or CO2 and hydrogen. Hydrogen comes from the water splitting, and then at the end of the tube you get the product that you want, say methanol, ethanol, or syngas, say, or polymer, anything that you want. So there are various ways of doing it. So one process is CO2 sits onto these surfaces, and say hydrogen sits onto these surfaces, and then CO2 and hydrogen has to come together, and when they come together they will react, and this reaction is catalyzed by the material that we put in the tube. The second thing that you need is energy. You will still need some energy. So that energy either come by heating, so you use electrical heating, or you can directly expose that material with a light, solar light, and that energy will come from the sunlight. Right. And then ideally this process is very simple. Ideally you mix CO2 and water, or CO2 and hydrogen, and end of the day you get the product that you want. Based on the catalyst, you can get methanol, ethanol, even ethylene or syngas. So catalyst allows you to tune what product that you want to produce.
Right. Yeah. And you mentioned that you use the nanomaterial and not the bulk material.
Yes.
What is the process of creating that nanomaterial, and what is the logic behind it? Why not bulk materials?
Yeah. So why not bulk means bigger size particles, right? If you see a sand on the beach is a bulk material. It's a SiO2 having say around 20-30 micrometer size particle. So they are very big. So now if I reduce the size of the particle, smaller the size, more will be the surface area, right? More number of atoms are on the surfaces. And the CO2 conversion is a process where CO2 has to interact with the atoms of the materials. Materials are made up of different atoms. Say if it is a gold, then it is made up of gold atom. So it's the atom which is the real catalyst. Right. So if I have more number of atoms onto the surface, then what will happen? More number of CO2 will interact, and then the conversion rate of CO2 to some useful chemical will be very high. Right. That's why we try to use a nanoparticle over the bulk particle. Now, how do we make them? One simple thought could be, I just take a gold ring and break it down until you get to nano, which seems impossible because nano is extremely small, right? So if you take a 1 here, you have to slice it by 1 lakh times to get a nano size, which is very small. So, although there are ways where you can take a bulk and then break it down to go to the nanoscale using laser and other techniques. But obviously, these will not be really a controllable, upscalable techniques. So, what we do is, we start from the atoms, right? Everything is made up by the atoms. So, we start from the atoms and molecules. Say, if you want to make a gold nanoparticle, I start with some gold salt, say gold chloride, and I put it in a round bottom flask or some conical flask, add gold salt, and then you break these gold chlorine bond by some reducing agent. So, what will happen? You get a gold atoms. So, many gold atoms then come together. Say 100 gold atoms come together and form 1 nanoparticle, 1000 gold nanoparticle come together and form 1 nanoparticle. So, we can dictate how many gold particle comes together and form the nanoparticle. That way I can make a 1 nanometer, I can make a 10 nanometer, and this is the typical way of making the nanoparticle starting from atoms and molecules.
Right. This is highly complex work, and one of the things that your group has achieved is the creation of a nanosilica material that is now being used by 150 other groups around the world, and that's a rare feat for something coming out of India. Could you tell us more about that?
Yes. So, this is known as a dendritic fibrous nanosilica. So, it's a silica, a nanoscale size. So, one is size, other is the morphology. So, it looks like a marigold flower, some sort of a dendritic flower. That's why we give them that name. So, see, one of the key aspects to develop the catalyst which capture and convert CO2 is I need to have a huge amount of surface area. More the surface area, more CO2 will go into that material, and then you can capture and convert. So, how do we improve the surface area? One is by reducing the size of the nanoparticle. Smaller the size, higher will be the surface area, but there will be limit. You cannot really go so small. And if you make really so small nanoparticles, then they have an issue with the instability. They are unstable. So, ideally you want to have a bigger particle, bigger nano size particle, and still have the high surface area. So, this is possible by creating the pores in the material. You create holes in the particle, and then the gas molecule can go inside those holes, inside those pores. But then if the material is porous, then what will happen? You have one entry from the top. You have to go in, and if somehow these holes are blocked, then your gas molecule cannot go in. So, in our material, we said, okay, let us not have pores, but it's some sort of a fibers coming out of these particles, and fibers are open to air, right? So, you can access the surface of the fiber from all the sides, and that's why it has a huge surface area. If you take a 1 gram powder in your hand, it's like a 1 football ground surface area in your hand. And so, that will have a huge ability to capture the CO2, which is the first step, and then convert into useful chemicals.
Right. So, you were talking about altering gold, and one of the things you have done is create black gold. Could you tell us a little more about how you created it and what its uses are in context of the CO2 conversion?
Yes. So, see, there are two functions a material has to do to convert CO2 into useful chemical. One is capture the CO2 and then stretch and bend the molecule, activate. One surface does that, but then you still need some energy. So, the same surface has to now take the solar photons, photon coming from the sunlight, and give that energy to activated CO2. So, one of the concept is these gold nanoparticles, which has electron cloud onto it, they try to interact with the electric field of the light, some sort of a resonance between the photon and the electron cloud of the gold nanoparticle. So, if I make say 10 nanometer gold nanoparticle, then it captures a light of around 520 nanometer wavelength. If I change the size of the nanoparticle, it captures another wavelength of the light. But to be a good catalytic system, what you will expect? You will expect that every photon coming from the sunlight, from 400 nanometer to say 1100 nanometer, should be captured by your material. More photon you capture, you will give that energy to the CO2, which is not possible by the normal conventional gold nanoparticle. So, then we came up with this concept that if you bring these gold nanoparticle closer, many of the gold nanoparticle closer, then these gold nanoparticles start interacting with each other. We call them plasmonic coupling, and that allows you to harvest every single photon coming from the sunlight in the visible range as well as the near IR range, from 400 nanometer to around 1100 nanometer. Now what will happen? If the material captures all the photon, it will automatically become black because nothing is reflected, everything is captured. So that's why the word black came into the picture, because the gold is still a gold. We haven't added anything into the gold. It's a pure metallic gold, but it is black in color because we changed the shape and the particle size distribution and the gaps between them such that now they capture all the light. So, and now once they capture all the light, that is the energy which is now stored in that nanoparticle. And my CO2 is also in that nanoparticle. So what will happen? That energy will go to the CO2, and then you convert CO2 into useful chemicals and products.
Right. So black gold essentially works like a tree. It takes sunlight, water, and CO2 and converts it into.
Exactly. We call it as it's a fancy term, artificial trees. Okay. Exactly like that. It takes water, it takes CO2, it takes solar energy and gives you the different product. Right. Exactly the way the tree does.
Right. Yeah. Another interesting aspect of your work is how you used nothing but water and magnesium.
Yes.
To create something called green cement.
Yeah.
Could you tell us more about that? And you also, some of your studies said that this has possible potential on Mars. So
yes,
a little more on that, please.
See, the cement industry is one of the industry which emits huge amount of CO2. Right. And obviously we need more and more cement nowadays because we want to be a developed country, which is a great idea. But then, can we reverse the process? Rather than while producing the cement, you emit the CO2, can I use the CO2 to produce the cement? And that's what we showed, that if you can use just a magnesium scrap, you don't need to have even a nanoparticle. A scrap magnesium, water and CO2, you can convert, you get a product which is called magnesium basic carbonate, which is actually a cement, green cement, with far better properties than the normal cement, right? And only challenge, obviously, we need to discuss is the cement that we produce is very cheap, but we have a huge penalty of emitting the CO2, whereas the cement that we produce, the green cement that we are producing from magnesium is expensive, very much expensive. So that has to be considered. So when we compare the pricing of a green cement versus a normal cement, we need to see that a normal cement, the conventional cement, emits the CO2, and here we are taking care of the CO2. So there's a new term is coming up like a carbon tax or a carbon credit, and that will hopefully make the green cement more commercially viable, which is not the case right now.
Right. That actually brings me to the next question. What are some of the major challenges you face in translating this work from your lab to, say, real world applications?
Yes. See, whatever we do in our lab is at a very small scale, milligram scale ideally. We make a small amount of powder of these catalysts, then we put it in some reactor, expose with CO2, light, and it works very well. But imagine if I have to use the same black gold I put 1 kg of this black gold in the tube, and then I want to expose every single particle of that black gold with light. Not possible, right? Because light penetration depth is limited. So only the surface gold particle will get the light. Rest of the particle won't get the light, right? So that's one of the challenge, which is more an engineering challenge, where how do I design a reactor which allows me to expose every single black gold particle by the light, right? So this is something we're working on. Another challenge is upscaling. Whatever we make in lab is again a milligram or a gram scale. Can we upscale? Especially in our lab, we are very confident that our material will be upscalable, because the way we synthesize, I told you, is very simple synthesis. You take some salt, mix it in a controlled way in a round bottom flask or a conical flask, and you upscale, you synthesize them. So this is very simple way of making the nanomaterial, and that's why we already showed magnesium process upscalable. We showed the DFNS upscalable from milligram scale to now around 40 gram scale, which is a huge jump. And now we are collaborating with various industries to upscale. And if the upscaling is successful, the challenge of translating this to industry is easy then. It's possible that you translate this to the industry.
Right. And what about other environmental issues that could have potential implications? So, for instance, can we use this for waste management at some level?
Waste management may not be, but see, one of the other challenge that we are facing is a plastic degradation, right? The waste plastic, right? So one can ask the same question, what do I do with the waste plastic?
Right.
So waste plastic is again made up of the carbon-based molecules. It's a polymer. So can I use these catalysts to break down the waste plastic to small molecules? Ideally, if you heat the waste plastic, they break it down, but the amount of heat required, the amount of energy required is so high that it will not be commercially viable process.
Right.
So what we are trying to explore the same catalytic system with some modification obviously to convert the waste plastic into their monomer, and then again you make the plastic, right? And this could be one of the way to use this material in environmental remediation.
Right. And would you say some amount of private involvement or investment or say climate tech startups could contribute to building this field and making it more commercially viable?
Yes, startup will play a very important role, right? Because we the professors or scientists are able to do things in the lab at a very small scale up to TRL 3. Industry wants something which is a TRL 6. Right, and then there's a gap between 3 to 6 which no one wants to do, which startup can take the challenge. And I think we should thanks to this government that they are really pushing forward for the startup. There are lots of schemes and programs which allows the scientists to start a startup. Unfortunately, my institute doesn't allow the startup for some other reason, but overall startup plays a very important role. Private funding is also extremely important. There are lots of the climate becomes so hot topic that everyone wants to invest. I'm interacting with many of these. Only issue I felt with these fund managers is they have a very little idea about the science behind it, the technology behind it, and they are just running behind the hot topics. Everybody said CO2 to methanol. Okay, we will also invest into the same process.
Right.
Nobody cares what do you do with the methanol, right? So I think these funds should also involve more scientific approach to decide where to invest. Otherwise, what will happen? They will invest into some of these so-called hot topics or hot technologies. They will fail and they will lose the confidence, and then the investment will suddenly stop. This happened. There was a survey where they studied many startups across the globe in CO2 capture and conversion. Majority of them failed. One of the reasons was they started with the wrong fundamentals, right? Because of the lots of investment and funds available, there are lots of scientists who just come out and say, oh, I produce methanol with the 10 rupees a liter, I produce syngas with this and that, and then lots of people invest. And then what we see at the end is the fundamentals were wrong, they were not properly evaluated, and then they failed.
Right.
Yeah.
Final question, sir. This is not an easy field. Research fundamentally has not been very easy to do in India. What is your key takeaways for young researchers coming into nanochemistry and nanomaterial work?
Obviously, doing a research, high quality research is extremely challenging, right? If you want to just do some cooking and publish a paper, that's very easy because there are thousands of journals nowadays that whatever you do, you get published. And then you can call that as a research. But real research, which is where you generate a knowledge which is unknown to us and which ideally at least improve the existing knowledge, is very difficult to do. You need extraordinary facilities, good funding, good students, and it's a group activity. Although I'm talking on behalf of entire my group, right? We do it together, and it's extremely challenging. But I think if one should be very focused, very motivated, and they have a big dream and a big goal of solving some big problem, without really worrying about the papers and recognition, it will automatically happen, right? That's what my personal experience is. There are always many challenges. I don't want to go into that. But if one is motivated and focused and work hard, this is the field where we work day and night, right? My students work day and night. There is no break ideally. Then the positive output automatically comes in.
Thank you so much for your time, sir. This was a very insightful conversation.
Thank you. Thank you very much for this opportunity to discuss with you, and thank you for coming to TIFR and have this very healthy discussion.
Thank you, sir. If you like this podcast, subscribe to us on YouTube or wherever else you get your podcasts.